We will continue speaking about the wave equation and its solution. Today we're going to focus on the solution of the wave equation in cylindrical coordinates, or when we have some cylindrical structure and we need to solve for the electric field and magnetic field inside this structure. There are some difference or some unique feature of the cylindrical coordinate system, as we can see here. In Cartesian coordinates, this unit vector, are they related to each other in any way? This AX, AY, EZ, are they dependent on each other? Are they related to each other? Is there any relation between AX, AY, EZ? They're totally independent. And they are, even they are constant. Any point in space, you will have the same AX, same AY, same EZ, in same direction. They will never change. What about the other coordinate and cylindrical coordinate or even spherical? Look at rho, phi, z. So if you move to somewhere else, would we have different arrow, different direction of arrow? Yes. A phi, EZ, only EZ is the same. In this case, it seems that these unit vectors are related. So what is the relation between arrow and A phi, these two unit vectors? Is there any equation that relates them? It seems they are independent, or in other words, are these unit vector rho phi z related to the coordinates rho phi z of this point? So this point has some phi, some rho, and some z. The unit vector rho, is it dependent on rho phi z of the coordinates of this point? What's the equation? The equation is clear from if you transform Cartesian to cylindrical, A rho is dependent on phi, cosine phi in the x direction plus sine phi in y direction. So different phi or different u will give you different rho. Is this equation clear? So you have ax here, you take ax in phi direction, in rho direction, it will be ax cosine phi plus sine phi y. So A rho does depend on A phi. What about the unit vector along phi, A phi? Is it dependent on rho phi z? A phi, look at A phi. Is there an equation like this that relate A phi to the coordinate system? Which is if you take A phi here, and if you assume that the same direction A phi can be taken here, it would be the same. You know the vector can move anywhere. So if you have A phi here, this angle will be, what's this angle? Will be phi, okay? This angle will be phi, assuming we are here on this, assuming we are in the YZ plane. So in this case, AY sine, AY cosine phi will give you A phi, and AX minus sine phi will give you A phi as well, because you will have AX here in the negative direction. So what we see here is totally different than the Cartesian system. The unit vectors here does depend on or highly dependent on the coordinate, mainly phi. Phi has nothing to do with rho, but rho has something to do with phi. What about EZ? EZ is the same. If you take the derivative, if you take partial rho, partial phi, what will be the answer? So if I take partial of this equation, partial phi, what should you get? You will get A phi. Look, if you take partial rho, partial phi, the derivative will be phi. Right? It will be minus x sine phi plus y cosine phi, which is A phi. And the d rho or d phi, both of them with respect to phi will be minus rho. If you take this, it will be like cosine phi in x plus sine phi in y. So d rho by d phi is phi direction or unit vector along phi, and the d phi by partial phi is minus rho. dz by phi is 0. It has nothing to do with phi. Actually, this concept is very important when we solve the wave equation in cylindrical coordinates. We will see that if you have like some electric field E, which is defined as E rho in rho direction, plus E phi in phi direction, plus EZ in z direction. Now we need to take partial E, partial phi. What should you get? What should you get here? It will be partial E rho, partial phi, right? Plus the other guys. Now you need to differentiate this guy and this guy. The differentiation here will hit both of them. If this AX, you will take it out. If it is AY, you will take it out. Easy, you will take it out. But here, you cannot take it out because partial A or partial phi is phi direction. So this is the main difference between, this what make dealing with cylindrical coordinate is not very straightforward, not like the Cartesian coordinates. We will face this problem when we solve the wave equation in cylindrical coordinates, as we have seen last time. So let's quickly wrap up what we said last time. So we are trying to solve the wave equation in cylindrical coordinates, okay, or cylindrical coordinates. Then we are going to use the same equation we had for lossless source-free medium. Then we will have the Laplacian operator for the electric field in cylindrical coordinates minus beta square in electric field also in cylindrical coordinates. Now what should we do next? Now I need to take del square Laplacian operator for A rho in rho in rho direction and E phi in phi direction, and Z in Z direction. How can I proceed here? I cannot take A rho out. If I can take this out like what I did in it will be easy. I will have three scalar equation. The only thing I can do here, which is a little bit straightforward, this part. This part I can, which already taken. I can take EZ out of this del square. If I take the EZ out, I will have del square E Z as a scalar. So it will be Laplacian to a scalar equal to beta square EZ. Then I can solve second order ordinary differential equation, which will be very easy. But the other two guys, I cannot do this for E rho and E phi. In fact, they are not equal. And these two parts are not equal because E rho should be differentiated with rho phi Z, as we have seen here. A phi should be differentiated. EZ can be taken out. So to go around this, to escape this dilemma, I will replace del square F, which is the Laplacian operator for the vector F, by grad divergence square minus kerr square, minus kerr, which is not very easy, but this is the only way I can do it. I have to get rid of the Laplacian operator by grad divergence and minus kerr. When we did this, we need also to have some trick here. The trick is that I'm going to assume that the electric field has some general form, E rho, E phi, EZ. Then I'm going to substitute this in the equation. I will take grad divergence minus kerr of this vector. I'm assuming this is the solution. This will give me, after doing the grad divergence, you need to do the differentiation and the kerr. After doing this, you can easily get three scalar equation. Three scalar equation that can be solved to find the component of E rho, E phi, EZ. Okay, is this clear? So I'm going to substitute this equation here in the wave equation. Then this will give me three equations in rho direction, in phi direction, and in Z direction. So I have now three second order partial differential equation. How can I solve this equation? Let's take this one. How can I solve this one? What is difficulty? Look at this. What is difficulty? I have two unknowns in the same equation. I have E rho, which I need to solve for, and E phi in the same equation. This is what makes it difficult. The other equation, again, I have E rho and I have E phi in the same equation. Like Ampere's law and Faraday's law. I have E and H, like coupled equation. These equations are coupled to each other. I need to get rid of E rho from this equation or E phi, and I need to have one equation, one unknown. Then I can solve it, which is very, very difficult. Mathematically, very difficult. The only equation I can solve in a straightforward way is this equation, to find EZ. I can use this equation, second order. This is a Laplacian operator for scalar EZ, like the same as we have done in Cartesian. I will solve it to find EZ. It can give me two solutions based on complex exponential and trigonometric function. The other two equations are extremely difficult to solve. But if I can find EZ from this equation, which is very easy, then I can use Maxwell equation to find E rho and E phi. And once I am done with EZ, I can go and solve for the other component, E rho and E phi, from Maxwell equation, from both Ampere's law and Faraday's law. So here now I will focus on EZ. I will forget about E rho and E phi for the time being until I find EZ. Then I can go for Maxwell equation and find E rho and E phi. So now I have Laplacian operator for a scalar quantity. This is a scalar, not vector. So I need to use the equation for the scalar Laplacian operator. Laplacian operator can work with vector and with scalar. Here I will use a scalar quantity, so I'm going to replace del square Ez by the 3 terms I have here. This will give me, I'm assuming now that psi is easy, this like easy. So this is the equation I have. Del square Ez minus beta square Ez, and I'm going to replace del square Ez by the Laplacian operator. I can solve this using separation variables, so I will have f g h, f a function of rho, g a function of phi, and h is function of z. So the problem now how to find f g h. I need to find these 3 functions which are independent from each other. So what I will do now, I will assume that psi is Ez, which is f g h. F function of rho, g function of y, h is function of z. I need to find h1. So I'm going to substitute this solution in the wave equation, and this will give me this equation here. Okay, once I do substitution, it will give me this equation here. Then I can get rid of this parameter here, gh. I can divide everything by fgh, like what I have done before. Now I have here some function. Look at this term. After I do the division, look at this term. This term is function of what? This term is based on rho only, right? And this term, rho, and this term, phi and rho, right? And this term, only z. So the 3 guys here will add up to a constant, to beta. Beta is omega root. This is a constant. So if this term is function of z, and no other terms are function of z, then I can assume this to be constant. It must be constant. Yet it looks function of z, but after you do the differentiation, it must be constant because it will add to constant. Do we have any z here? Look here, do we have any z here? There is no way. So this could be or should be a constant. If you have any z here, you cannot do this. You cannot assume this. And that's what we have done in Cartesian also. We were able to assume this constant because each term was independent from the other terms. So I'm going to replace this by what we call minus beta z, which is the z component of the propagation or the phase constant. This is the phase variation along z direction. In fact, beta will be like a vector that has different components. One of them is beta z. Now, this will make things easy because once this term equal to beta z, I can solve for h. I can find h. This h can be found from this assumption. What about the other term? Can I do this here? And like what I did here. Can I do this? Can I assume this to be constant? Why? Because it has two independent variables. It has rho and phi in the same equation. So what should I do? Get rid of rho square. Remove this rho square. Multiply everything by rho square. So this will be rho. This will be rho square. Am I right? And this will be rho square. And this will be rho square. Multiply everything by rho square. If we get rid of rho square, this part now will be dependent on phi only. Do you have any other phi in the equation? Look everywhere. Do you have any other phi other than the here in this circle? So I can assume this to be constant, which is what we call minus m square. Any constant. Okay? So the reason I can do this because this term is function of some single independent variable, which is phi, and there is no other function of phi any other where in the equation. Okay, if I have phi anywhere, this will not work. You will notice that here I assumed this term, which is dependent on phi, to be minus m, some unknown. But here I assumed beta z. You remember beta x, beta y, beta z? So I assumed I have some vector component of the propagation constant along z, but for phi, I didn't assume like beta phi. I didn't call it beta phi. I called it m or n, whatever. Why I'm doing this?
Because phi direction is constant.
So let's go back. I'm going to multiply everything by rho square. So I will get rid of rho square. Now this part is dependent only on phi. So it can be assumed to be minus some constant, which we call it m square. Okay, I didn't assume any propagation along phi. Does this make sense? So there is no beta phi. There is nothing called the beta phi. Because this propagation constant is based on the phase variation along a certain direction. Where is the direction is moving to infinity. We can do this for x. The wave can move along x, right? Along y, along z. But there is no traveling along phi. Phi is like periodic movement. So if you come at phi 0, then you go 2 pi, you have to come to the same phi, right? So there's no phase accumulation. In fact, this m will turn out to be the order of the Bessel equation. We don't have beta phi because phi is not direction of propagation. In cylindrical coordinates, direction of propagation can be along the axis of the cylinder or even along rho. We can have propagation along rho. But along phi, it's like periodic movement of the field, and the field must come to the same place, the same value every 2 pi. So it's periodic, so we don't have phase variation along phi. Or we don't have wave traveling along phi. In fact, it will be like sine and cosine along phi direction. So now this part will help me to find G. So I can find H and G the same as we did in Cartesian by using this assumption. I can easily find G. It will be either complex exponential, e to the power minus jx or minus j phi, or sine and cosine, trigonometric function. Very easy. Now what is left? What is left in this equation over there? I have done with H, G. I need to find F. If how can I find F? Your question last time. How can I find F here? These two guys, which seems to be function of rho, seems to be. Can we assume this to be constant? Then solve the same as we did for H and G? Hmm? Why?
We have rho square from the other term.
Because we have rho in the other terms. If we don't have this rho square, then this can be assumed to be constant. In fact, this part here, if you take everything to the other side, it will be a function of rho, clearly function of rho. So I cannot assume this to be constant. It is not constant. Okay? I was inaccurate last time. So this is not a constant. So how can I go around this? How can I find F? I need to find F to complete the solution. I did this, I need to find this guy. So it will be a special differential equation, which is Bessel differential equation. And if I replace here, if I take beta or rho square, if I bring this here, then take rho square common, it will be beta square minus beta z square, which can be assumed to be, I can assume this guy now, or it will be like beta rho square. So the beta vector will have two components, beta z and beta rho. We don't have beta phi, because there is no wave propagation along phi. And here I have rho square minus m square, so the equation now can be simplified. I can replace this guy by, I can replace this, beta square minus beta z by beta rho. So the equation will be like this, which is the same as a Bessel differential equation. So we can solve it using the standard solution for Bessel differential equation based on Bessel function or Hankel function. Or you can go through the solution. You can derive the solution for this using Bauer series or Bauer summation of the same form as Bessel function, actually. And the m here is the order of the Bessel function. M, which we have assumed from the phi part, will be the order of the Bessel function. You remember Bessel function has order starting from 0, 1, 2, if it is integer, or assume integer here. And the equation related beta to the component beta rho and beta z is called concentrating equation or characteristic equation. Do you remember why we call it a concentrating equation? What's the meaning of concentrating equation here? What's the meaning of this word? Concentrant equation. Concentrate on what? What are the constraints we have here? This equation is relating the vector propagation constant or phase constant to the component beta rho and beta z. So if beta rho and beta z to change in space, they must add up to beta. So beta, or the direction propagation vector, will be the same magnitude anywhere in space. So anywhere it will be like on the surface of a sphere. Okay, it will have the same magnitude anywhere. So the solution for this equation will be based on Bessel equation, and then we will continue the solution like what we have done. So now we can solve for h. H will be either exponential or trigonometric function. This exponential will represent traveling or standing wave. This form will be traveling wave because it has e to the power g. E to the power g means you have traveling wave. And this equation, if you sketch in time domain, if you take this sketch versus time at different time, it will be like moving up and down, standing wave. And for m or for g as a function of phi, it will give me two equations as you can see here. So the two equations are, this equation we can call traveling wave, but we're not going to use it. It's just a mathematical solution. This equation is called periodic wave. So look at cosine phi. It will go and back and come back to the same point every 2 pi. So this is called periodic wave, not standing wave. It's periodic because it is based on phi. Phi is rotational angle, not like x moving from 0 to infinity. Phi has limits from 0 to pi, and you have to 0 to 2 pi, and have to come back to the same point every time. So in our solution, and if you have cylindrical structure, most likely the solution will be the periodic wave. For the f, we need to use, we have no solution but to use the Bessel differential equation. And in fact, I will have two solutions, one based on Bessel equation, first kind, second kind, the other based on Hankel function, first kind, second kind. What are the difference between these two guys? The difference is the behavior of the function. So this guy is will represent standing wave. This guy will be traveling wave. This guy is standing wave. This guy will be traveling wave. Okay, this is nature of this function. So I will have FGH. F will have two solutions, standing, traveling. G will have two solutions, traveling wave and periodic wave. This periodic wave, and H will have two solutions, standing and traveling wave. So based on your structure, you can assume one of these solutions to be your solution based on the problem at hand. H is the Hankel function, is the complex combination of the Bessel function. So H is the Hankel function, is J Bessel function of first kind plus J Bessel function of second kind. The second kind of Hankel function is the same equation, but we have here both to become negative. The first kind will represent wave traveling in negative rho. The second kind represents wave traveling in positive rho. Positive rho means away from, if you have cylindrical along the axis, this has to be used if the wave is moving away from the axis. If the wave moving inward, you will use the Hankel function of the first kind. So for circular waveguide, assuming we have hollow metallic tube, and the wave is moving along the axis, so we need to choose solution for HFG. What should be the solution? For F, should we choose standing wave or traveling wave? It's a long row, right? It's a long row. This means it will get reflected, so it will move back and forth between the walls. So it will bounce. So it will be standing wave. And for H, it will be standing wave or traveling wave. The wave is moving along the axis, so it will be traveling wave along H or along Z. And for G, you have two forms, periodic and standing. So periodic and traveling. So it is periodic is along phi. So this will be the solution. Standing wave along rho, periodic wave along G or along phi, and traveling wave along Z.
Standing wave will be only on the
only in the rho direction here.
only on the surface,
On
or
the-
it will exist within the inside and the external.
With inside. Because you have two components here. You have like forward wave and reflected wave. So they will combine together to form the standing wave, like two opposite components. Same as transmission line. But here is a long row. So this is a summary of what we have said last time. And this table is a nice table. It shows all the combination you can have for traveling wave, standing wave, evanescent wave, attenuating traveling, and attenuating standing wave. So it's a summary of all the possibilities you can have in your solution. So can stop.